We've seen the analogy to the hash table in 2 dimensions, so now let's talk about the tree equivalent. So recall that one of the big advantages that search trees over hash tables is that they explicitly track the order of items. Now we never really leverage this to any great degree, but it allows us to do a bunch of things. Like for example, if I wanted to find the minimum item in a binary search tree, it would take theta log n time. We would just go down the left side over and over and over until we don't have any more places to go, and we're done. But in a hash table, of course, finding the minimum item, it could be anywhere. So it takes theta n time. There are other examples that you can try out with binary search trees, other features you can add. So for example, it's pretty easy to modify a binary search tree to support operations like rank, where you say, give me the 5th largest item or whatever. And if you're curious how that would work, you can see the optional textbook, but essentially binary search trees, they're all about order. So they let you do cool ordered operations. And just like we had with finding the minimum, it is generally impossible to do that efficiently in a hash table. So it is also theta n. So what we're going to do now is we're going to exploit similar properties of trees so that we can speed up operations like nearest or range finding. Okay? So let's start by looking at 2-dimensional data and why it's not just trivial. So imagine that we have bodies in space, like say Mars and Earth. Earth has position 1.5, 1.6, that's x and y respectively, and Mars has 1.0, 2.8. Okay? So in a binary search tree, we need some notion of less than to build our tree. And if we're considering both points, then we can't compare both at the same time. So the most natural thing you could do is just pick one. So if I do that, in the x position, we would say that Mars is less than Earth, right? It's to the left. But if we look at y position, then Mars is greater than Earth, since it is above. And so an x-based tree for Earth, an x-based tree for our planets looks like this, whereas a y-based tree looks as we see on the right. Okay. So the point here is just to specify that comparison, somehow, we need some total ordering for our objects. And if you have 2 different dimensions to consider, the easiest thing you can do is just consider only one of those dimensions. So let's see why that causes us some trouble. We could do this, right? But the problem is that we'll lose some information about the ordering, and I'm just going to give you a very quick look at why this matters. So if we took 6 arbitrary points, I just made them up, and I inserted them into a binary search tree based map that maps point to letter. Okay. So for example, I'm mapping a to the value, -1, -1 to the value a. Okay. Now if I do that in a binary search tree that is ordered by x coordinate, this is what I would end up with if we did this set of insertions. So for example, a is inserted as the root, and it effectively has value -1. And the y coordinate is totally ignored for the purposes of building the binary search tree. B comes along, and since 2 is bigger than -1, it goes to the right. 0 is greater than -1, but less than 2, so it ends up here. 1 is greater than -1, less than 2, greater than 0, and so D is 1. And this picture I'm showing on the right is just showcasing where the points are actually located in space. So if you take your points and you just insert them into a binary search tree, which orders based on x coordinate, this is what you end up with. Now, what we'll see is that because it's in a tree, we can actually optimize a little bit. Okay? So for example, let's suppose someone asks us, what are all the points that have x coordinate that is less than -1.5? Well, since a, this root right here, it effectively splits the space into points that are less than -0.1 and less than -1 and greater than -1, then we don't have to explore this right side at all. So in other words, we start searching this tree. We look at the root. We say, okay, are you inside this rectangle? No. Okay, could one of your left children be in the rectangle? Well, yeah, that's all the stuff that's less than -1, and this rectangle is asking for all points that are less than -1. So we should look on this side still, but we will not need to explore this right-hand side. So when we actually do some kind of exploration of this tree, then we do not even need to look at the letter B, just not necessary. Okay? So we can say we are going to ignore it, and that process of cutting off a search of a tree early is called pruning. So you will not even need to go over here. Okay? Now, the reason I bring this up is that if we instead did the opposite, that is, we ordered based on the y coordinate, we get a little bit different of a binary search tree. So here we insert a, with coordinates -1 and -1, and so that ends up being the root. Then we do 2, 2. Well, 2 is bigger than -1. And again, just as before, now we're basically only using the y-coordinate and totally ignoring the x-coordinate for the purposes of building the binary search tree. So next along comes 0, 1. 1 is bigger than -1, but smaller than 2, so that ends up there, and so forth. And maybe I'll just go to this last point. So how this one ended up where it is 2.5 is bigger than -1. It is also bigger than 2. So now, if we do that exact same range query, where we say, what are all the points less than -1.5, we can't do any kind of pruning. So we look at the root, we say, okay, you're not smaller than -1.5 in the x-coordinate, but now, because the A is effectively splitting the space into a top and a bottom, there's no pruning that we can do. We can't say, it is possible, and indeed it is the case, that both the left side and the right-hand side have a point that satisfies the condition. In particular, E, which is on the left, and F, which is on the right. So here, our choice of which dimension to use made a really big difference in terms of how much the tree we needed to explore. So we can do better than this. That's the good news. This is the bad news, that if you just use one coordinate, it's not so good, but we can do better, and that will be the good news. And so the basic idea, which I'll go through in the next video, is just have 4 neighbors, one for each of the 4 different directions you can go. Okay? And I'll go through the details in the next video.